All right, so in all the examples we've done so far, we've our hit detection's all been in 2D, but what about working in 3 dimensions? What about hit detection with 3D? Now, it's not as simple as just doing above, because the nice thing about what we did earlier is that we have a 2D space and a 2D mouse coordinate, right? And so we can move them into the same coordinate system and work with those. With 3D, there's a big question, and that is, what Z value does the mouse get? Right? So we had to think about that. Mouse doesn't have a Z. What do we do with that? And when you click on a point, you don't want to just click on the image plane, anything straight behind it, right? So one way to think about it is that the mouse point becomes a line or a ray. It becomes a line representing all Z points underneath it. At least within the view volume, right? Okay, so the mouse point becomes a line representing all of it. Let's see if I can draw something like this. You know, you could imagine, here's your view volume, you have your mouse here. Cool. You click on a point. Now your view volume, as we know, is much bigger, and you have this view frustum like that. So then your mouse click actually becomes the line like this, right? And so if I have a circle over here, and then a triangle down here and a square up here, then the circle or the sphere is what gets intersected with the mouse. So this works actually quite well, but as you can imagine, there's a lot of math involved. We'll come back to this a bit later. Now the second option is to work in raster coordinates. So instead of adding a Z value to the mouse and going into the world, into the 3D scene, we forget that and we go the other way. We say, you know, let's flatten things onto the raster first, and then let's work in this space. But again, it's not trivial. It's not straightforward because of several reasons. We're just working in pixels by that point, or flattened objects and colors. It might be difficult to trace it back. Okay. First problem we have is if there's overlap. If there's overlap, which object? So object is hit. So you can imagine if I have a scene like this. This is my eye here, my near and far planes. You can imagine having an object here and an object here, and then when I'm working in raster coordinates, where's my mouse? Here, you see that as I flatten the raster, things onto the raster, two things will be under the mouse point. And so we have to determine which one did we hit. One option is Z sorting. Let's just sort everything by Z value. Okay? And that's a good idea if things are parallel to the plane, but just like we learned earlier with the painter's algorithm in 3D, it doesn't work if objects are not parallel to the view plane. And I'll draw what that looks like. So in this case here, you imagine you have an object like this and an object like that. I guess I should draw my planes in. Again, and you have a mouse pointer coming through, it can be pretty tricky to figure out which one should be hit and which one shouldn't, okay? When you're doing it with math, it gets very complicated. The math gets complicated very quickly. So you might be thinking, well, maybe we could start doing something like our Z buffer, and we could leverage the Z buffer and maybe keep track of what object we've hit, and if another one comes by that's closer, let's remember that one, right? That's basically what the solution is. Thanks, Siri.
In chemistry, a solution is a special type of...
Okay. Not sure how that happened. But we can do this using the graphics pipeline. So let's think about how to do that. So this next unit I'm going to go over is how to solve this 3D hit testing using the graphics card. Or maybe I should say the graphics pipeline. Okay, so cool. So let's do that. So recall that we have this frame buffer. I'm going to draw a frame buffer. I'm going to label it. I don't have enough room. So we have our frame buffer. And we're going to go along and fill in pixels, right? Now remember that while rastering, we actually keep track of the Z values in another buffer. While we are rasterizing, we keep a second buffer called the Z buffer to remember the Z coordinates. Okay, it helps us, in NDC. This helps us with sorting, helps us with draw order, but it's also useful if we want to invert our transformations. We can go back into, from the pixel back into the world. Okay, so this ensures draw order proper, I should say. And this supports inverting the pixel transform. So we can go back into the world where the pixel came from. So this is our Z buffer. And as you remember, as we're drawing those pixels, we write our Zs in here. If we draw a pixel at the same spot and it has a closer Z, we override it and update our Z buffer. Okay. So what we can actually do here is we can add a third buffer while we go along with this. And this third buffer is called a hit buffer. So the solution to our problem, we can add a third buffer called the hit buffer. And let me explain how it works. So what we do is at each location, at each pixel, I should say, in the frame buffer, we have a corresponding Z buffer entry, but we also now have a corresponding hit buffer entry. Okay, so what we do is it stores some kind of object identifier, okay? Some unique, that's really messy, some unique object identifier. Right? That then tells us what object is actually drawn at that spot. Okay. So the way that it works is, in code you often do something like this. Before you draw something, you can set ID and you give some number you want. And that's nice because you get to make up these numbers. And it's also nice that it's not tied to one triangle or one primitive. If you're going to draw a building that you want to hit, or an enemy or a hand, you could say, okay, set ID to my hand ID, draw a bunch of geometry, and all that geometry gets that ID. So when I click on it, you know you hit the hand. So I set some ID I draw my object, and then I set ID to something else, to another number, and you can make these numbers up yourself. It's very common to have like just a counter where you go, get number is counter plus plus, so each one has a unique number. It's just an integer. It's really easy to implement. So you set some ID and you draw some other object. So every object that you want, that you care about, you can give a unique ID to. So then when we're filling in the frame buffer, we manage the Z buffer. At the same time, in the corresponding entries, we put in these identifiers, okay? And then this is really nice because then when you click on the screen, you don't have to do any of the mess we've talked about with math. You just go, okay, what pixel is this? I have the hit buffer. Yay, right? Look in the corresponding pixel entry. I get a number. I know which one I've hit. If it's a 0, it's a background or whatever, right? So this is really, if you can manage this, makes picking becomes really easy, built into the pipeline, okay? Just click on the screen, you look at the hit buffer under that location, you get the number, you know which object you hit. It's not perfect if you're doing things like where in the object I hit, then you require some math still to figure out where you are, but you know which object you hit, okay? This is actually really common in older video games. If a third buffer isn't available for whatever reason, so let's say you have a primitive video card and you have limited memory, or you can't modify how it's drawing, then what you'll see some people do is they'll actually just do another draw pass. So they'll re-render the whole scene, except what they'll do is, one, don't blit the screen so we don't see it. 2, we replace all the materials. So we remove materials and use flat shading. Okay, and then we set the color to be the object number. So it's really cool. So you're like, all right, you know what? These object numbers? Yeah, that's my color, 24. Sure, doesn't matter, just a color. And so then you can pick, you render the scene, go through the whole pipeline. Instead of putting it to screen, you grab it into memory. Now you have a hit buffer, right? So you can do that. It works really actually quite well. And you might be thinking, geez, it's expensive. It's a lot of work. Well, it is, but if you're rendering at 60 or 100 frames a second, you only need to do this when someone clicks. And people are not going to be clicking any more than, I don't know, 5 times a second tops. Then it actually doesn't take a lot of work in the grand scheme of things to generate redraw that current frame twice, once giving you a hit buffer, okay? And you don't lose much performance because of how rarely you do this. So that's how that works. It works really well for simple setups. Okay, but there are some complications when you start getting into more complex scenes. So for example, what do you do with transparency? When you're mixing colors from front to back. Okay, this complicates your Z buffer too, and we didn't really get into that. But with the hit buffer, I'm seeing like 2 things are contributing. Do you keep the closest one? Like that actually makes things a little more complicated. Shadows. That's modifying the pixel. You're drawing a shadow, but that's not part of the object. Okay, right? So it sets the fragments, but it's not part of the shape. It should not be a hit. In fact, we should hit the thing behind the shadow. So there are a lot of problems with this. It's a really cool, simple technique. You'll still come across it when people talk about, oh, we just use a hit buffer. It's really common in 2D games, 2D platformers, that kind of thing, where you can imagine comparing a hit buffer. It's really simple. So that's how that's done. So, okay, so maybe now's not a bad time to take a break, and we'll come back and we'll learn about some other solutions to this problem of hit detection and picking.